So on this question that we are given, it is to sketch the graph of y is equal to tan x for x is greater than or equal to 0 less or equal to pi over 2, and the area enclosed by the graph. X-axis and the line of x is equal to pi over 4 rotates about x-axis. Show the area and the representative strip that you use to calculate the volume, and that was 2 marks. And from there, the volume and the moment of inertia. So we want to figure out how this strip is given, how does it affect the volume, and how does it affect the moment of inertia at the same time. So you must be careful on questions of moment of inertia and the volume. They can give you a question like this where they combine the volume and the moment of inertia, or it can be just straightforward from the function to the moment of inertia. Does not mean that this volume here affects the moment of inertia, because you're not given like in terms of mass. It's just calculate the moment of inertia about x-axis. Okay, so according to the function that we're given, this is the graph of a tan. Y is equal to the tan of x that we are given from 0 to pi over 2. Remember, pi over 2, that is 90 degrees. And the graph of tan, as we know, it does not operate at 90 degrees. At 90 degrees, that is an asymptote. We do not have a value of tan 90 degrees. That is an asymptote. So meaning to say, this graph operates at 0, 45 degrees, and we know that 45 degrees, that is pi over 4, which is at 1. At pi over 2, which is 90 degrees, that is, we have got an asymptote. We do not have a value there. We move on to another value, 90 plus the 45, which is 135, and so on. Having values and so on. But in this case, we are just focusing on what is happening between the first part of the graph. So it's just something like this. All right, remember, it's supposed to be a piece of this nature from 0 going up, as if it approaches, it does not meet this pi over 2 because that's an asymptote. So it was going to be another section, and so on. So at pi over 4, it corresponds with 1, which is fine. Okay, so in this case, that is our graph. Y is equal to the tan of x. And this is enclosed, the area is enclosed by the graph. The x-axis, meaning to say the x-axis is part of this. The line x is equal to pi over 4, meaning to say x is equal to pi over 4 is involved. So meaning to say, if the area is enclosed, covered by this graph, covered by the x-axis and this line, this is the section that is remaining. This part is not covered, so you're not going to talk about that. So the section that we are talking about is this one. And according to the limits that we have from 0 to pi over 4, considering the limits for x, we can have the strip best represented for x. So in this case, they're saying when this rotates about x-axis, like the volume or the part of the section that you're given, so it is an advantage because the rotation and the strip, they are on the same platform, like they are corresponding to each other. So that is, we can use the disk method to calculate the volume, which is the one they're asking on 5.22. To calculate the volume, when the area described in this question 5.1 rotates about the x-axis. So if it rotates about the x-axis, and according to this strip that we are given, the strip is for x, the rotation is also for x. The strip is for x. So it means we can use the disk method. This is corresponding to each other. So that's the disk method. Okay, so remember your disk method, we talked about this. The volume with respect to x is going to be given by pi, the integral of y squared with respect to x, with the limits a and b. The disk method is the normal method, remember, that we are used to. There's no adjustments there. It's just a matter of substitution Y is our f of x. So that is the integral of the limits from 0 to pi over 4. And y is the tan. So that means we've got tan x squared like this. But remember that tan x squared like that is same as tan squared x. You can just write it that way with respect to x. This we can integrate direct because we have that from our formula sheet. Remember, we have this integral, the integral of tan squared ax with respect to x is given as 1 over a tan ax minus x plus c. So in this case, there is a 1 tan squared 1x. So meaning to say this, we can just integrate direct is going to be 1 over 1 tan ax, which is just tan x. So that is tan x minus x plus the constant of integration. So since we've got the limits, there is no need for us to indicate the constant of integration. So that's it. That's it, guys. We can integrate this. After integrating, substitute the limits. I said, whenever you've got these pi, whatever that you're given, these are radian values. So your calculator is supposed to be in radians. In radians. You're working with a trigonometric expression. There's this pi. So make sure that your calculator is in radians. So let's substitute the upper limit. Tan pi over 4 minus in place of x, that is pi over 4. So this is for our upper limit minus what we are having on the lower limit. Place of x, we're going to substitute a 0. That's tan of 0 minus a 0 like this. So that was going to be our our lower limit. So that is how these questions sometimes might be given as, and all you just need is to substitute and so on. So you're going to simplify this. That was going to be pi, and the whole of this part was going to give us something like 0, 0.2, 1, 4, 6, and so on and so on and so on. So if you multiply to this pi, that was going to be 0, 0.674. Remember, this is volume measured in cubic units. So the disk method, it's a direct method. This is what we are used to. It's a question. If a question is given like this, it's an advantage to us because we are used to this part and we just have to apply the same consideration that we have. And also even for the moment of inertia, because they are saying it's about the x-axis. Of the solid obtained when the area in this rotates about the x-axis. So in this case, the strip that we are given, like for the moment of inertia, it is the same strip that we are given for x that we used for volume. So if you see that consideration happening, that is, you are given the strip being for x. You are calculating the moment of inertia when this is rotated about the x-axis. And the strip that you're given there is for x. I said it on the difference between the hollow section and the laminar concept, a circular lamina. These formulas that we are given here are the ones that are for direct approach when the rotation is for x, the strip is for x. When the rotation is for y, the strip is for y. This is exactly what is happening here. So you are not applying or using anything special. The formulas are already there. It's different when you are given the strip for x like this, then they ask you to calculate the moment of inertia when it is rotated about the y. I talked about that on the hollow section where you use the shell method concept. In this case, there is nothing like that. You take your formulas as they are from your formula sheet. We are given this as half of the density times pi the integral of y to the exponent of 4 with respect to x, where this y here is a function of x. So we are going to substitute this with what we are given from 0 to pi over 4. So y is what? That's a tan. Remember what I said about an exponent. So it's same as tan to the exponent of 4x with respect to x. Guys, at this stage, this is no longer about the moment of inertia that we are having there. It's about your normal integrals. How do you integrate this tan to the exponent of 4? Remember, on our trigonometric part of our integration, a tan to the exponent of 4 of this nature, we are going to use the identity of the tan squared x, which is equal to sec squared x minus 1. So from this identity, how can we express our tan? So the tan means there's a product there. So ix is going to be half of this, that is the integral of the product of tan squared x and another tan squared x. Remember, a tan, you expand it. You don't raise to the exponent of 2, you expand tan times tan. Knowing what you need from there, which is to substitute one of these tan with equivalent identity. So we can just leave one of these and substitute. So guys, this is your normal algebraic, your normal trigonometric integration. They can, remember your question number 2. They can even ask a question like this just to integrate a tan on its own. So I'm not going to talk much about this one. Make sure that you do your revisions on your normal integrals. How would you integrate this? All right, so remember there you're going to expand, use the substitution method on the first part. All right, so let's say the tan and the sec, that is going to be tan squared x, sec squared x. The tan and the minus 1, that will be minus tan squared x. Okay, so you're going to integrate with respect to x. This first part, we need the substitution method. So we can just try to apply our substitution method. What can we choose to be our u? So that if you are to consider there, you must cancel something there, a sec squared. So you can just let u to be a tan. So that the derivative of u with respect to x is sec squared x. So that's making x dx the subject. It is going to be cross multiply, then divide is going to be du over sec squared x. So meaning to say, if you were going to substitute here, it was going to be the integral of tan, which is u to the exponent of 2, sec squared x times, in place of the dx, because there we are going to have this dx. But dx is now given as what? As du over sec squared x, like this, where this can cancel to this, and we have got u to the exponent of 2 with respect to u. So let's integrate to the exponent of 3 over 3. So we can substitute our u there, which is the tan. So this was going to be tan to the exponent of 3x, everything over 3. All right. So the first part, we can integrate using the substitution method. And from that part, like we have seen, we are going to obtain tan to the exponent of 3x everything over 3 minus the integral of tan squared that we are given. Tan squared, I think you have to consider also your formula sheet, guys. The tan squared, you are given that. Actually, we talked about this when we integrated that one for area. I mean, for the volume. You still remember? It's only that I erased, but when we're talking about the volume there, we integrated a tan squared and we got something like tan x minus 1. So remember there, when we integrated this, so it is gonna be a minus like this. Then when you integrate tan squared, remember it gave us a tan x minus x. So if you multiply by this negative that is outside, is gonna be negative times tan, which is negative tan x, negative times negative, that's a positive x. Okay, so that is what you're going to have with our limits from 0 to pi over 4. So we can substitute and simplify further. So in this case, remember on the substitutions now, in order for you to make sure that you obtain exact values, this is same as tan pi over 4, everything to the exponent of 3. So on your calculator, that will be another bracket there. Remember, your calculator is just going to open its own bracket. All right, everything over 3 minus, that is tan in place of x, pi over 4, plus in place of x, pi over 4. So this is our upper limit. We subtract the lower limit in this case when this is a 0. So guys, substituting a 0 there, it was just going to be a 0 throughout. So that was going to be a 0 throughout. Okay. Yes, you can substitute, no problem. I'm not saying it's wrong, but tan, remember tan is 0, it's a 0. So that was going to be 0 throughout. So if I am to simplify each inside, combine everything that you are given, you are going to obtain something like 0, 0.18, 0, 0.11, 8731, and so on and so on. So multiply to this 1 over 2 times pi. So if you multiply to 1 over 2 times pi, it is going to be 0, 0.187 times the density that is remaining there. That is to the exponent of 5. You are not told, write this in terms of the mass. We just calculate the moment of inertia when that whole area is rotated about the x-axis. So meaning to say, you just integrate, leave your answer in terms of the density. Why worry about the mass while you're not given about when the question is not specific, it's not specifying like in terms of this unit. It is just calculate the moment of inertia. So the formulas there, they work out, they are used when these two correspond, like I said before, when the strip and the axis of rotation are corresponding to each other. But if they're different, then you consider the formulas of a hollow cylinder, which is where you use the shell concept. I talked about that, or make sure that you watch the part of that hollow sections so that at least it can help to know the difference on the formulas, because those formulas you're not given, these are the ones that you're given. So you have to know them by heart.